Okay, so we'll talk about functions now and programming functions. Okay, and so in R, functions have the form where you have the name of the function. Okay, and the function accepts a few arguments, and then it evaluates this stuff. Okay, and then the last line will be will tell it to return something here. Okay. And so the name is the name of the function, and then and the result is the output, and that can be assigned to an object. Okay, this is the thing that that gets returned when you run a function. Okay. And so you know, if there's only one line, you can leave off the curly braces. So generally, all of this stuff is sectioned off with curly braces. But we can create a so here f is a function that basically squares things. Okay, and so here f is a function that accepts an argument x, and what it's going to do is it's going to multiply x times x, and that's it. There's no curly braces. And if we ask R what is to create a list of f, then it will say the object is a function of x, and if we ask R what is the type of, so remember this would always kind of return back, you know, it would say it was logical or integer or something like that. Here it's telling us that it is a closure. Okay, and so those are they are objects, and you can do object related stuff. Okay, and so here this is we're creating function 2, which is a function that returns a function. This is kind of, it's a little bit weird looking at. Okay, and so if we ask, so this is a function that accepts the argument x, and then it's going to accept another function y. Whoops. Okay, and then so if we just ask f2 evaluated at 1, what it returns is a function of y. So it plugs the 1 into x here, but then what gets evaluated is this function y, where it's going to say, okay, now I have function y x plus y. Okay, so so this is, R is a functional programming language, meaning you can have, you know, kind of functions that return functions. Okay, and then so in order to evaluate this, we would say f2 of 1. Okay, this part up here returns this, and now we would return, we're plugging in the 1 into this function y, and then it evaluates those two and it returns the value 2. Okay, so it's a little bit strange, but most of the time our functions are kind of this form, where we're not returning functions. We'll talk about functional programming later, and it is a powerful thing that R can do. Okay. All right, so you can explicitly use the command return to say this is what I want it to return. Okay, or if you don't explicitly use the word return, it's going to just return the last statement in the function. Okay, so so both of these will return x times x. This one is explicit, and this one is implicit. So a lot of times you'll see functions written. If you delve into the code of things written in R, sometimes returns are used and sometimes returns are not used. And if they're not used, it's going to return the last line thing there. Okay. You can have it return multiple values. Okay, so here we're creating a function f, which will return the value itself, the value squared, and the value cubed. And so when we run the command function f on 2, it returns 2, 4, and 8. Okay, and here instead of just combining them together with the command C, we are returning a list where we've thrown them all together, and we've given our list names. Okay, so we said, you know, f of 2, what is x? X is 2, its squared is 4, and its cubed is 8. Okay, so it's pretty much the same thing as before, except rather than a combined thing, a combined vector, it's a list. Okay, and so many functions in R return things as lists. Like if you've ever used the LM function, linear model function, all of its results are lists, right? And that's why you can do like LM $. I'm sorry, you output the results of the linear model into something called results, and then you can do like results $ coefficients, or results $ residuals, or things like that, because the output of that function, the LM function, is a huge list. Okay, and you know, because so certain functions can be vectorized, and it's going to return all of this stuff. Okay, we can define argument names. Okay, and so here we're creating a function xyz, which, and all we're doing is we are just gonna paste them together using this text here, and so the output of this function is just this character string here. Oops. And so and the character string is that. Okay, and so we can, and when you define the function this way, you can use the argument names to kind of put the things in any order that you want. Okay, so you know, so certain commands or functions that you might have used is, you know, what is the normal density or something like that, and when you call that to R, it's expecting the first element you give it to be you know, the value you're looking up, and the second element to be the mean, and the third element to be the standard deviation, or things like that. And you can give it in that order and it will work, and that's what it's expecting here. So 1, 2, 3, it's expecting it in the order x, y, and z. You can define it as, well, first I want to give you z, and then x, and then y, and then it's going to arrange those appropriately. It's going to match the argument names up to what they are. Okay, and you can just define one of them, y is 2, and then it will kind of match up the remaining ones in their order as well. And so here we're doing this, and if you give it something and you say I want m is equal to 1, it's going to say, it's going to error out and not evaluate anything. It's going to say, you've given me an argument that we don't use at m. Okay, you can also give it default values. All right, so that if that argument is not defined, it will just evaluate these things. Okay, so f, when we give it default values where everything is 1, it's going to print out x is 1, y is 1, and z is 1. Okay, and then here we give it a single option, or argument 2, it's automatically going to plug that into the first argument. So then we get x is 2, y 1, z 1. Okay, or you can specify, I want the third item z to be 3, and then we have that. Okay, the scoping question, this is important in that, you know, you can run a function, and here the function is a function of x, and so it's going to take x and it's going to try to evaluate this. It's going to try to add x plus y. Now when it looks for y, it's going to see that y is not defined within the function. Okay, and because it doesn't find it inside the function, it's going to move to the next variable scope out. All right, and that's going to be, in this case, our global scope or global environment. And so when we give it f of 3, it's going to plug 3 into for x here, because f is a function of x, and then it looks for the y. It doesn't find it. It finds it out here, and it plugs in 1. Okay, I kind of just want to show you just some of the other stuff that happens here. Okay. Oh, this is exactly what I was going to show you. I forgot that I wrote this. So here we're defining the function g, okay? And we say y is 1, and we got the function g of x, okay? And within this function, we are defining y equal to 2. And then we're going to say do x plus y, and when we evaluate g of 3, it's going to say, okay, well, I know x is 3 because that's what we've given it here. And then it says, okay, well, what's y? Oh, inside this scope, y is 2. So it's going to put those two together and then return back 5. Okay. And if I were to go back and ask, what is y though? So let me just kind of clear this out here. So I've got y is equal to 1, and we're going to define all of this, and we're going to ask run g of 3, and then we ask what is y? Again, y is still 1, okay? So even though inside the function we've called it 2, we've decided to assign the value 2 to y, it only affects inside the scope, and it doesn't affect outside the scope. In the environment, y remains equal to 1. Okay, so here, g, when we run g, it's it returns back 5 because y is equal to 2 inside that scope and only that scope. Okay. It says variables defined within a scope only exist in that scope for the duration of this scope. So if variables exist with the same name outside of the scope, they are separate and do not interact with the variables inside the scope, nor are they overwritten. Okay, and that's what we saw with that y equal to 2 versus y equal to 1 outside of the scope. Okay, and it says you can think of a function as its own separate environment that only communicates to the outside world via the arguments and the output expression. Okay, and that's true. All right, so basically it's like its own world where you are feeding stuff through the arguments of the function, and then when the function's done running, it returns an output, and that goes back out into the environment. All right. The only exception is using this super assignment. Okay, so normally you just have kind of like a single arrowhead, but if you give it a double arrowhead, this is the super assignment, and that will assign it to the higher scope. Okay, so okay, and it says, for example, if you execute the command rm is equal to list remove everything, it only deletes the object that have been defined inside the function. So you can run this inside a function, but it doesn't delete everything in the global scope. Okay, but so here, for example, this is the regular assignment, and we'll see that this is exactly what we have before. Okay, but here I can do super assignment. Okay, and what this does, so y is 1, and I'm now going to define my function. And now when I run the function, okay, so right now y is still equal to 1, but when I run this function, the super assignment here says don't affect my local copy of y, but affect the y that's in the higher scope. So when I run this, we see the y gets affected outside the scope, and the y out here is now equal to 2. Okay, so that's the super assignment that alters things outside of the scope. Okay, and there are times when you use super assignment, but you got to be careful. Okay, because you generally when you run functions, you're expecting only things inside that thing. So here we've got functions nested inside functions, and so we can see what is x and y and z. Okay, within the function f, we are running y is 2, and within that function we define another function where z is 3, and we're going to return the results of that. Okay, and so when we run f, it returns back 6, but then if we ask what is x, y, and z, those are still all equal to 1. Okay, all right. Here I've changed y to be the super assignment here, okay, and the z function to be super assignment, and then so here it searches out the higher scopes, okay, and rewrites those things, okay, and so here we ask the same thing, we get the same results, 6, 1, 2, and 3, but then we asked what are x and y and z now. They've been overwritten because it's looking for this in the higher scope, and it doesn't find it until it gets up to here, and it redefines x, y, and z out here. All right, and so it says, when should we be using functions? We want to encapsulate a small reusable piece of code, and you know, generally you want your function name to be descriptive of what the function performs. I know in all of our examples we just called them f and g and things like that, and that's not good naming habits. Okay, if you're going to have a function that squares values, you'll probably want to call it squaring or square or something like that. All right. You know, these are suggestions, and says the function should be simple enough to be quickly understood, and you know, the smaller you write your functions, it's easier to deal with, and it's better to just change code in one small bit of a function than try to locate it everywhere where it needs to be changed. Okay. This is Infix Operators. We probably don't need to worry about this. Okay. So, you know, the operators like plus, you know, we do 3 plus 5 and we get 8. It's technically you can run it this way, where you have an infix operator, and you kind of use the what is this thing called? The back quote? The I don't know. The accent character, and you can apply that to a infix operator, okay, and it returns what we have, okay. And so here we've defined a new infix operator as a function, and it runs such as this, okay. And then but if you're going to create infix operators that are different from the standard operators that exist within R, you have to have this % here, okay. All right. Write a computer program to solve a problem. Oh, okay. Yeah, programming strategies. Okay, let's see how much time we have. So I was going to kind of run through maybe some examples of things we can code. And so, you know, if your next homework assignment, and I suppose I can post it now already for next week's assignment. You know, it'll ask you to program a few different functions that might be a little bit challenging. And so you want to think about those problems that you're trying to program and try to figure out a general idea of how to solve that problem first, okay? Translate your idea into some kind of implementation, and then try to just make sure that it works the way that you expect it to work, okay? Otherwise, you gotta fix it, okay? And so the top-down design approach is to kind of write out the steps in you know, just a few number of steps, and then with those steps you can then expand each of them into a smaller number of steps that can be turned into actual code. All right, so let's so our first example, we'll take a look at this idea of bubble sort. Have you guys heard of bubble sort? Yeah? No? Have you guys already had to program bubble sort? Oh, okay. Well, let's see. Okay, so it's a simple algorithm that basically you give it a string of numbers mixed up, and then what you want the function to return is the numbers put in order, sorted. Okay, and what it does is it evaluates pairs of numbers. Okay, and it swaps the numbers if the number over here is is bigger than the number over here, right? Because we want to go from least to greatest. So, we just look at these two pairs and the two numbers, and if this one's bigger, then it's going to arrange them as such. Okay, it's going to switch their position, and then it keeps going through the list. So here's an example. Okay, so it's looking at, it's just kind of comparing these two things. Okay, and it says, 7 is bigger than 2. I'm going to swap these two things. Okay, moving on. 7 is bigger than 4. I'm going to change those things. Okay, and then it says, okay, we've put this in its position. Or let's compare 3 and 1. Okay, this is 3 is bigger. Let's compare these two, and it's gonna say that's fine. Okay, and then it looks at these two and it says, oh, this one is bigger than that, so that we have to swap. This thing is bigger than that, so we're gonna swap. Okay, and it's gonna just keep doing this until it is satisfied that everything is met. Okay. So it's going to swap these, and so on. This is this little GIF or GIF is from Wikipedia, so we can thank them for their nice little animations, and it just goes through. Okay, so anyway, this is how bubble sort works. All right, so how can we define how this stuff works? Okay. The coding. Okay. All right, so let's we're gonna let's just create our vector here of, so I'm gonna set seed 1, and then I'm gonna define x as basically sample 1 through 8. Okay. All right, so let me just get rid of G and Y. Okay, so I've got X, and X is just this vector that's not in order here. Okay. All right, so let's define how we can code up bubble sort. Okay, so we're gonna create a bubble sort function. Okay, and our function is going to accept the argument x. Okay, and so x is the vector that we're going to give it. Okay. All right, and so I'm going to just kind of write out in words what we want it to do. Okay, and so we're going to so first I'm going to just say bubble sort function to sort a vector least to greatest. And what we want it to do is we're going to define it into a few steps. Okay, we're going to say look at the first pair of numbers. Okay, and then and we're going to see test to see if item I is greater than item I plus 1. Okay? If yes, okay, we switch item I and item I plus 1. And if not, move to the next pair. Okay, and then so repeat the comparison for all items in the vector. Okay, and then repeat until we are done, right? So how do we define we are done? Okay, so this is where we have to think about this. So the first time we run through it, we're going to keep moving the we just compare these numbers and we swap them if this number is bigger than this one, and then we move to the next one and we keep swapping. And so when we do that, the largest number is going to end up in the last spot. Okay, so if we have 8 items, we will have to do it from, we'll have to compare I to I plus 1 for items 1 up through 7, right, until we get to the last one. So basically from I, the length of our vector, 1 less than that. So we're going to start from 1 up through position 7, okay? And then we're going to run through it again, but this time, because we know the largest item is now in the last position, we only have to go from 1 through position 6, okay? And then we do that again, and then we go 1 through position 5 until we are done. Does that kind of make sense? So, you know, the first time, or I guess the first sweep, we go from position 1 to the second to last element. So basically length minus 1. Okay. Next time, next sweep, go from position 1 to basically length minus 2, so on and so forth. Okay, so let's figure out how to do this. Okay, so I'm going to so we'll first start, and we'll just we'll start with, we'll just do for one sweep, okay, and then outside of this we can build some hierarchy. Okay, for one sweep we'll just go we'll make a for loop which goes from I, for I in basically 1 through the quantity length of x minus 1. Okay, so this is for our kind of our quote first sweep. Okay, and what we're going to do is we're going to just check. So we'll say if we're going to do a comparison, is x at sub I greater than x sub I plus 1, okay? And if it is, we would switch those things, okay? So what we're going to do is we're going to just create kind of like a holding position. So I'll do I'll call hold, and we'll stick x sub I in there, and then we're going to swap, reassign x sub I to the value that's in x sub I plus 1, and then we're going to put x sub I plus 1 into that. We'll take the value that we've held. Okay, and so this will work through the first sweep, right? Okay, and otherwise we just keep going on here. Okay, so now we have to think. You know, what do we do next? So what we want to do is for the next sweep, we want to basically do the exact same thing. Okay, so what we're going to do is we're going to put this loop inside another loop. Okay, whoops. And then so we're going to create a loop where we're going to do each of these sweeps. Okay, so this was for the first sweep. Okay, and then so now we have to do repeat the sweeps so that the entire what do you call it? Vector sorted. And basically we can just rerun this entire loop, okay? But how are we going to modify this loop so that it will work not just for the first sweep, which goes from 1 through basically position 7, but the next time it'll go from 1 to position 6, and then 1 to position 5, and so on and so forth, okay? So what we can do is we can think, so this length x minus 1, we can call this, we're going to call this something like j, okay? So j should go to, so I'm going to just kind of call this, create a comment. J should go to 7 the first time, and then j should be 6 the next time, all the way until, repeat until the last time we run it, j will be what? All the way down to 2, right? Because that, when you do the final comparison, you're just going to compare position 1 to position 2, okay? So for this loop, what we're going to do is instead of length of x, we're going to start with j minus 1, okay? And then so our for loop here is going to be it's going to be j in basically the vector where we are creating a sequence that starts at 8 and goes all the way down to 2, okay? So we're going to start at length of x and go all the way down to 2. Actually, yeah, repeat until, yeah, j is 2 so that down here it works, okay? So this should do it, okay? So we're repeating the sweep so that, you know, j goes to 7 the first time, okay, or not, I guess technically it's I goes to 7 the first time, which is length minus 1. And then I goes to 6 the next time, and so on and so forth, okay? And so that will be j minus 1. And so this goes from 8 to 2. All right, and let's just make sure this loop closes off. And then so what the once we're done with all of this, we this is all within a function, right? So the last thing we want to do is we want to return our sorted function x. Okay, so all we have to do is just, last line is just return x. All right, let's see if this works. Okay, so I'm gonna give it, and maybe it doesn't work. So we have x is this unsorted thing, and I can do bubble underscore sort, and we'll run it, and it seems to have worked. It seems to have worked. Let's see if y is let's do 1 through 100. Okay, so why is this mess here? Let's try bubble underscore sort y. Did that work? Why is my It looks correct to me. Okay, so you know, and this is a sorting algorithm that that works. It's not the most efficient sorting method, but it works, and it's just simply by comparing pairs of numbers, and you just have to make sure it runs through there. Okay. Let's see. I was going to do an example of merge sort, but I think we will run out of time. Okay. And let's see. Let's view this image by itself. So here is, it basically splits the list, and it keeps splitting them until splitting the lists in half, and then sorting those two together. Well, okay. We won't have time to do this, but okay. So I guess that will just be something you have to check out. I can post up code for how merge sort works, or maybe I can make it part of your homework assignment. I'm not sure. As far as debugging goes, okay, when we are trying to, when you run code, rarely does it work correctly the first time to do it. Okay, and so here are just kind of the guideline steps for figuring out what your bug is. Okay, and then so first of all, identify that a bug exists. Okay, and so this comes through kind of testing to make sure that the code is behaving the way you expect it to behave in every situation that you can think of. Okay, and then if it doesn't behave the way you expect it to, see if you can figure out exactly under what conditions or under what circumstances does your code fail. Okay, and so that's trying to make the bug reproducible. And so if you can figure out exactly what set of conditions cause your bug to fail, then you might be able to identify the source of that bug. Okay, sometimes R will spit out error messages, and sometimes these error messages are cryptic. Sometimes they at least give you a clue or hint as to where the problem or the bug lies. Okay. This is just a quote on how debugging works, but it's the idea of try to break up your code into little chunks and making sure that each chunk behaves the way you expect it to. Okay, and if every little chunk does exactly what they're supposed to do, when you put them together, they should be working together correctly. Now sometimes you've got different chunks that work correctly, but when you put them together, things seem to break down, and that's probably because the output of one chunk doesn't match the expected input of the next chunk. So you kind of want to just make sure you've got this correct flow idea for getting all of your pieces to work together. Okay. Here's another strategy, which is if you've got maybe you've tried to make your code more efficient, and when you tried to make your code more efficient, that's when things start to break down. Okay, then in that case, use the old code that might be inefficient that works, compare it to the new code that doesn't work, and try to piece out little part by part what exactly works correctly and what doesn't. Okay, and so it's all about trying to just hone in on exactly what is working and what isn't. There's this idea of edge cases. Edge cases being like, so 99% of the time your thing works, but then when you plug in a 0, it doesn't work, or when you plug in a very big number or a very small number, it doesn't work. And so you've got to a lot of times You got to figure out what is allowed and what isn't allowed, and maybe you have to include some kind of thing that says if someone's trying to plug 0 into my thing where I know, somewhere in there I'm going to be dividing by this number where you're not supposed to be dividing by 0, you want to have some way to catch that thing and say, you can't plug 0 into this thing, okay? All right. There are a few different ways to try to trace and identify your bug. Somewhere in the, throughout your code, you can stick in a bunch of print statements that says, like, at this point in time, the value of this variable inside my code takes on this thing. And you can see as the code is running line by line when that value changes and if it's changing the way you're expecting. Okay, so as you're running code, you can say, is x equal to this thing, and you can print it out. And so, this might not be the best way to go, but you can see line by line, is it working the way you're expecting it to work? And so, that often works in a loop. You can have a print statement somewhere in your loop to make sure that with every iteration, the values are being updated the way you're expecting them to be updated. Okay, and so these are just different, hints or tips to keep in mind as you're writing code and if you're running into problems, which is almost always going to be the case. If you can write code correctly the first time, congratulations, but it probably won't work that way forever. So anyway, we'll see you guys on next week on Monday. I'll try to get the second homework assignment posted by then, and so you can go ahead and take a look at that. All right.